Welcome to Physics 192, General Physics 2, covering the topics of electricity, magnetism, optics, electrical circuits, and nuclear physics. This course builds upon the content of Physics 191, General Physics 1. I'm your professor, Gerard Blanchard. If you're taking this course for credit, then please refer to Moodle for your course syllabus, homework, exam dates, and all communications about this course. Regardless of whether you're taking this course for credit or not, I recommend that you watch these videos with pencil and paper and a calculator in hand, because the secret to learning physics is active learning. Physics is a skill that you learn through practice, so the more active you are in watching these videos, the better you'll learn it. If you have any questions at any time, you may email me at gerard.blanchard@southeastern.edu. Let's begin with electric and magnetic fields and forces. This portion of the course deals with electric charge, electric fields, magnetic fields, electric energy, electric forces, magnetic forces, and so on. The first thing to realize is that electric and magnetic forces are field forces, which means that physical contact is not necessary for a force to be exerted. You should already be familiar with one field force. Let me demonstrate that for you. I'll demonstrate electrical field forces using ordinary Scotch tape. What I will do is I will take one piece of tape, and I'm just folding a little handle here so that I can pull it up easily. I'm going to stick that piece of tape to the desk. I'm going to take a second piece of tape, and I will place that on top of the first one. And then I'll make an identical second preparation. Take a piece of tape, stick it to the desk, and place another piece of tape on top of that. Now what I'm going to do is I'm going to pull up the top two pieces of tape. It's important that I'm pulling up the two top pieces of tape, because that way when the tape gains an electrical charge from being pulled apart, the top two pieces of tape will have the same charge. So I'm pulling up the top piece of tape from here, and as I pull it up, it will gain an electrical charge. I don't know whether it's positive or negative, but that doesn't really matter at this point. I will take this piece of tape, I'll stick it over here, and then I'll take the second top piece of tape, and I'll hold it in my hand. I'm going to bring, you just saw some attractive electrical forces there. Now we have the two charged pieces of tape, identically charged pieces of tape, and I'll bring them together, and you can see that they repel each other. The two like charged pieces of tape repel each other. And one other thing that you can see is that the force with which one pushes the other away is dependent on the separation between them. The closer the two pieces of tape get, the more repulsion they have. I'll bring it away, and then as I bring it in, you can see we have a stronger repulsion between the two. So those are two like charged pieces of tape. Once again, I don't know if they're positive or negative, but they have the same charge, whatever it is. Now for my second demonstration of electrical forces is I will take both the top both the top and the bottom pieces of tape, and what I'm doing right now is I'm uncharging them as a whole. So when I pull the two pieces of tape apart, one will have one charge and the other will have the other. Okay, now I'll take this piece of tape and stick it over here. And now I will bring this other piece of tape, which has the opposite charge, and I will bring it close to here, and they will attract each other. And they'll attract each other without touching. Let me demonstrate that again. Let me try the two other pieces of tape. Okay, so I'll pull them apart. So they each have opposite charges this time. Now bring them close, and you can see that they are attracting each other without even touching. They don't have to touch each other to attract each other. And once again, the attraction is inversely proportional to the separation of the two. The closer I bring them, the greater the force of attraction. So that's our first example of electrical field forces. When we have two charged objects, they will either attract or repel each other without even touching. And they attract and repel each other through the action of an electrical field, which is going to be the topic of the first topic that we're going to get into here. For my second demonstration, I'll demonstrate magnetic forces. What I have over here is I have a sort of teeter-totter, a seesaw that has a wire on it. I'll show you the wire in a moment. And the wire is connected up to this electrical power supply, and I'm going to run a current, an electrical current through that wire so that the electrical charges in that wire are moving. I'll go ahead and do that. I'll turn it on and apply some current. And I'm going to take a magnet, and this is the north end of the magnet. And I'm going to take the magnet and I'm going to bring it close but not touching the wire, and we should see the effect of a force. And there you go. You can see that there is a downward force on that wire. There's a downward force on that teeter-totter, on that seesaw. Now that is the effect of the north end of the magnet. If I were to take the magnet away and turn it around and bring the south end towards the wire, we'll see actually the opposite effect. So once again, without touching the wire, I'm exerting an upward force on the wire or on the seesaw. So that is an example of magnetic field forces. Once again, it is the magnetic field of this magnet that is exerting the force on the wire without even touching. Okay, let me turn off the current and I'll show you a little bit closer what that board looked like. As you can see here, there's a wire on this board, and there are cables connecting this wire to the power supply, and so a current flows through this wire, which means that charges, electrical charges, are moving, and that's something that we will talk about very shortly. Now, that's an example of electrical field forces, magnetic field forces. You should already be familiar with one field force, and that is gravity. As a demonstration of the gravitational field, I'll hold up this pin and I will let it go. Once I let it go, something pulls that pin to the ground. What happens is that as we learned in Physics 191, the Earth creates a gravitational field around itself, which exerts an attractive force on any other mass. So the Earth creates a gravitational field which is pointing downward, so that when we put another piece of mass in that gravitational field, it feels a downward force. And that is what causes the pin to go from not moving to moving, gives it a downward acceleration. Now let's look at the equation for the gravitational force. The equation for a gravitational force is that the gravitational force vector is equal to the mass of the object feeling the force times the gravitational field vector. So F vector sub g is equal to m times g vector, where m is the mass of the object feeling the force, g is a gravitational field created by all other masses, in this case the Earth, and g has units of newtons per kilogram. So that would be newtons of force per kilogram of mass in the object feeling the force. The electric force has a very similar equation, and that is F vector sub E is equal to Q times E vector, where F vector sub E is the electric force vector, Q is the electrical charge of the object feeling the force, and E vector is the electric field created by all other charges. Now, G, the gravitational field, had units of newtons per kilogram, or newtons of force per kilogram of mass. E has units of newtons per coulomb, or newtons of force per coulomb of electrical charge in the object feeling the force. So coulomb is the unit of electrical charge. That is the basic metric unit of electrical charge. Let's talk a little bit more about electrical charge first. Protons and electrons are the source of all charge in ordinary matter. Objects become charged, such as the tape, becomes charged by gaining or losing electrons. Electrons are usually more mobile than the protons are. Protons and electrons, the magnitude of the charge of protons and electrons is the same. And we give that a symbol of little e, which is equal to positive 1.602 times 10 to the minus 19 coulombs. And we call that the elementary charge. So E in this case doesn't stand for electron, it stands for elementary charge. And so E, little e, is a positive number. Remember that. Don't let that confuse you later on. So little e is positive 1.602 times 10 to the minus 19 coulombs. And that is the elementary charge. So a proton, which has a mass of 1.673 times 10 to the minus 27 kilograms, has an electrical charge of plus E, or positive 1.602 times 10 to the minus 19 coulombs, whereas an electron, which has a mass of 9.107 times 10 to the minus 31 kilograms, has an electrical charge of minus E, which would be negative 1.602 times 10 to the minus 19 coulombs. So protons have positive charges, electrons have negative charges. Our other subatomic particle, the neutron, has a mass of 1.675 times 10 to the minus 27 kilograms. The neutron has an electrical charge of 0. So neutrons are neutral. So protons, every proton has a charge of plus 1e. Every electron has a charge of minus 1e. And all other objects become charged by either gaining or losing electrons or possibly protons. But the important thing is that the charge of any object must be a multiple of the elementary charge. So you can only gain or lose whole numbers of electrons or protons. So all other charges are a multiple of little e, which is 1.602 times 10 to the minus 19 coulombs, where coulombs is our basic metric unit of electrical charge. So going back to our equation for electrical force, where we have F vector sub E, or electrical force vector, is equal to Q, the charge of an object, times E vector, the electric field. This is a vector equation, which means that we have three separate equations. We have an X equation, a Y component equation, and a Z component equation in this equation. So that means that the electric force in the X direction is equal to the object's charge times the electric field in the X direction. That means that the electrical force in the Y direction is equal to the object's charge times the electric field in the Y direction, and the electric force in the Z direction is equal to the object's charge times the electric field in the Z direction. So we will have to consider X, Y, and Z, all three dimensions in this course. So every vector equation now becomes three separate component equations. And we have the electric force vector is equal to charge times electric field vector, gives us three equations where we have the X, Y, and Z component of the electrical force, the X, Y, and Z component of the electric field, and the charge, which is a scalar. So charge does not have X, Y, or Z components, just as mass didn't. Okay, we are ready to begin working exercises. Let's start off with this question. The electric field across a cellular membrane is 1.0 times 10 to the 7 newtons per coulomb directed into the cell. And this question has two parts. The first is, if a pore opens in the membrane, which way does the electric field push sodium ions? Which would be Na+. And that is a sodium atom that has lost one electron, so now it has a net positive charge of 1e. So which way does the electric field push the sodium ions? Into the cell or out of the cell? And the second part of the question is, what is the magnitude of the electric force on the sodium ion? So, as we did in Physics 191, I advise you to begin by drawing a diagram of this situation, listing everything that you know and don't know, and then writing down the equation that is appropriate to help you answer this question. So, I'm going to give you a little time to get a head start on me. Remember, be active. Okay, let's start with the diagram. I will draw the walls, the cell wall, and we'll make a pore. And so this would be inside the cell. This would be outside. And I will draw some coordinate axes. I'll make this my x-axis, and I'll make this my y-axis. So here's, as we said, here's inside the cell, and here's outside the cell. And we are told that the electric field across the membrane, this is the membrane, the electric field is directed into the cell. So we have an electric field directed into the cell, and it has a magnitude of 1.0 times 10 to the 7 newtons per coulomb. And we have a sodium ion. I'll draw that in the pore. There we go. And the charge on the sodium ion is plus E, which is equal to 1.602 times 10 to the minus 19 coulombs. And we can further say that since the electric field is pushing into the cell, or it's pushing to the right, which we've called our x-axis, this electric field is actually the x component of our electric field. So the x component of the electric field is 1 times 10 to the 7 newtons per coulomb. So our equation for electric force is force vector electric is equal to Q times the electric field vector. And the component that we're interested in is the x component. So that would say that force EX is equal to Q times EX, or the electric force in the x direction is equal to 1.602 times 10 to the minus 19 coulombs times the x component of the electric field of 1.0, we'll call it 1.00 times 10 to the 7 newtons per coulomb. So FEX is going to be 1.602 times 10 to the minus 12 newtons. So we've answered what is the magnitude of the force, which is 1.602 times 10 to the minus 12 newtons. And we've also identified it as being in the positive x direction. This is the x component of the force, and it is a positive number. So if the electric field is pointing into the cell across the membrane, then the sodium ion will feel a force in the positive x direction, or into the cell. So for a positive charge, the electric field pushes that charge in the direction of the electric field. So since we have a positive sodium ion, the electric field being directed into the cell pushes that charge into the cell. So the direction of the force on a positive charge is in the direction of the electric field. Okay, so that answers the question that we were asked. Let's ask another question. In a cathode ray tube, electrons that are initially at rest are accelerated by a uniform electric field of magnitude 4.0 times 10 to the 5 newtons per coulomb during the first 5 centimeters of the tube's length. Then they move at essentially constant velocity another 45 centimeters before hitting the screen. And the question is to find the speed of the electrons when they hit the screen. Okay, so once again, I would like you to draw a diagram, list all of your knowns and unknowns, and this question is actually a kinematic question. It's also a non-equilibrium question because the electrons are initially at rest, but they don't remain at rest, they accelerate. So we should consider both Newton's second law, that the acceleration of an object is equal to the force on the object divided by the mass. And we should also consider our kinematic equations, our equations that describe how objects move. And these were all covered in Physics 191. So please start working on this question, and I'll give you a little bit of time to get a head start on me. Okay, I will start drawing my diagram. There's my electron, and it starts to move. I'll say that it starts to move in this direction. It's accelerated in that direction. We'll call that direction our x-axis. There's our x-axis. And we'll start the electron off at x initial is equal to 0 meters. Vx initial, it starts from rest, so that's also 0 meters per second. And the time at which it starts, we'll call that t initial, we'll call that 0. We'll start our stopwatch when the electron starts to move. We also know that the charge on the electron, Q, will be minus E, or minus 1.6, we'll call it 1.60 times 10 to the minus 19 coulombs of charge. The electron, the next time that we know something about the electron, it's at x final is equal to 5.0 centimeters, which I can convert using 1 meter is the same as 100 centimeters. Cancel my centimeters. And we see that x final is 0.05 meters. The speed of the electron, Vx final, the speed of the electron at the 5 centimeter mark, we don't know. We also don't know the time at which the electron reaches the 5 centimeter mark. So t final is also unknown. And so is our acceleration. Acceleration is also unknown. We do know that there must be a force on the electron, an electrical force on the electron. And since the electron is accelerating in this direction, in the positive x direction, the electrical force, Fe, also must be in the positive x direction. And we also know that the magnitude of the electrical force must be equal to the charge of the electron times the magnitude of the electric field. Okay. So now, well, that gets us to x is equal to 5 centimeters. We're told that after the electron reaches the 5 centimeter mark, it travels on at constant speed, which means that our acceleration is equal to 0 over here. And so it hits the screen 45 centimeters past this, so that would be x is equal to 50 centimeters, and Vx, we don't know. Okay. Well, we have here a kinematic situation. We have an electron that is moving. So we will use our kinematic equations that we learned in Physics 191, and we have to pick the kinematic equation based on what we don't know and don't need to know. We are interested in the electron's final speed. And if we're interested in the electron's final speed, then we need to have an equation with speed in it, but we're not asked for the time at which the electron reaches the 5 centimeter mark. So we would pick our kinematic equation that doesn't have time in it. And that equation, so we need our x kinematic equation. And so that would be Vx final squared minus Vx initial squared is equal to 2 times the acceleration in the x direction times x final minus x initial. And we do know most of what's in this equation. We know Vx initial. We're looking for Vx final. We don't know Ax, but we'll figure that out separately. We know x final, and we know x initial. So as long as we can figure out Ax, we can use this equation to tell us what the speed of the electron is right here. We'll figure that out using our non-equilibrium equation or Newton's second law. X non-equilibrium, and that tells us that the acceleration in the x direction is equal to the force, the total force on the electron in the x direction divided by the electron's mass. So we do need the mass of the electron as well. Let me get that. The mass of the electron is 9.109 times 10 to the minus 31 kilograms. Okay, that's why I gave this information to you earlier, because we will need this. Okay, so the acceleration in the x direction is equal to the total force in the x direction divided by the mass. And there's only one force on the electron, and that is the electrical force. So we can figure that out, divide by mass, get the acceleration, put that into here, and we'll be able to answer the question that we're asked. Okay, so let's work with this. The acceleration of the electron in the x direction is equal to the electric force in the x direction on the electron divided by the mass. So the x component of the electrical force would be the electron's charge times the x component of the electrical field. That's exerting the force divided by the mass. And we were told that the magnitude of the electric field, let me write that in here as well. We were told that the magnitude of the electric field is 4.0 times 10 to the 5 newtons per coulomb. We're only told the magnitude. We weren't told the direction of the electric field, but we'll figure that out in just a second. Okay, so what do we have here? We have the acceleration in the x direction is equal to the electron charge, which is negative 1.60 times 10 to the minus 19 coulombs, times the electric field, which has a magnitude of 4.0 times 10 to the 5 newtons per coulomb. And we'll divide all of that by the mass of the electron, which is 9.109 times 10 to the minus 31 kilograms. Now quickly, for those of you who might not be familiar with my style of working through equations, I only write down the numbers in an equation with the assumption that we're working with basic metric units. I don't write in the units for an equation when we are using basic metric units. So if we're dealing with coulombs, newtons per coulomb, and kilograms, I won't write down the units so as to avoid some clutter in the equations. Okay, now one thing about this is we know that the acceleration is in the positive x direction. We know that from the way that we've drawn our diagram. The electron is here, it's at rest, it starts picking up velocity in the positive x direction, so the velocity of the electron is increasing in the positive x direction. That tells us that the acceleration also has to be in the positive x direction. So, with that, we know that AX has to be positive. And since mass is positive, since the electron's charge is negative, we can infer that the electric field must be in the negative x direction. So I'm going to draw in a minus sign here. So when I multiply these two negative numbers, I get a positive acceleration in the x direction. So I'm going to come back up here in our diagram, and I'm going to draw in the electric field in the negative x direction. We know that the electron is getting pushed in the positive x direction. It's a negative charge, and the force on the electron is opposite the electric field. So it's an electric field in the negative x direction that gives us a force in the positive x direction, which gives us an acceleration in the positive x direction. Okay, all we have left to do is to work out our numbers. And so we have a negative 1.6 times 10 to the negative 19 coulombs times a negative 4 times 10 to the 5 newtons per coulomb divided by 9.109 times 10 to the negative 31 kilograms, and that gives us an acceleration of positive 7.03 times 10 to the 16 meters per second squared. So we have a very large acceleration in the positive x direction, and now we can add that into this equation up here. So we have Vx final squared minus Vx initial, which is 0 squared, is equal to 2 times Ax, which is 7.03 times 10 to the 16 meters per second squared times x final, 0.05 meters minus 0. And so we have Vx final squared is equal to 2 times 7.03 times 10 to the 16 times 0.05, and that gives us 7.03 times 10 to the 15, and so we'll take the square root of that, and we'll have Vx final is equal to the square root of 7.03 times 10 to the 15, which gives us, let's see, 8.38 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7 meters per second. So that is the speed of the electron at the 5 centimeter mark. We're told that the electron travels at constant speed for the remainder of the distance. So we know that the ultimate Vx final will also be 8.38 times 10 to the 7 meters per second. And that is the answer to the question we were asked. So you can see from these two examples that what we're doing is we're applying what we learned in Physics 191, namely kinematics, Newton's second law for non-equilibrium, and we're applying them in the context of a new force, the electric force. We'll be doing many more examples of that next time. Until then, think physics.